In this video, we'll be covering part 2 of isomers of coordination compounds. So we are looking at isomers that have transition metals in the middle in particular. The one we've been talking about were the structural isomers. So isomers, just in general definition, are compounds that have the same chemical formula, like the cobalt, NH3 2 and then Cl2 or something like that. And all of them have that, but they have different structures. And the one we've been talking about before was the structural isomer. In the focus of this video, we'll go into the stereoisomer. Stereoisomer, they subdivide into geometric isomer and also enantiomer. The geometric isomer also subdivides into cis and trans, and there's another one, and we'll talk about that later. So let's define stereoisomer first. Stereoisomers are atoms that have same connectivities. They have same connection with the central transition metal, but they have different spatial arrangements. So if a ligand is, like let's say fluorine is here on the right, now all of a sudden fluorine is on the top. So they have special different spatial arrangements. Geometric isomers are they're ligands that are arranged that are differently around the metal ion, and in particular cis and trans is a one type, and here's an image that could give you a better understanding. So something like this, okay, this one has cobalt and that's in the middle, so let's kind of put that in the middle. Cobalt, they're both cobalts in the middle, and the green one represents chlorine. The rest of the ligands, that represents NH3. So this is an NH3. Okay, so let's look at the chlorine. Chlorine, well, there's two of them, and within one coordination compound, and you see that there's cobalt chlorine on one side, and on 180 degree on the opposite end is a chlorine. Something like this we consider to have a trans geometric isomer, whereas one that is a 90 degree of each other, we refer to them as cis. Now look that we're only comparing with just the chlorine, not the ammonia. The chlorine are just the two of the same ligand compared to the rest of the ligands, right? So you want to look at the ones that are in two in a pair. They're the one that's going to determine whether this is going to be a cis or trans geometric isomer. Now let's go into the other side of the geometric isomer. Remember, geometric isomers, there's cis and trans, and there's what is called a FAC and MER. The FAC and MER, well, example will look like this. So say you have a transition metal in the middle. So this is my transition metal. TM represents transition metal. And these little round purple and the teal spherical circles, they're the ones that going to represent the ligand. Well, this one particular ligand, the purple one, they're all in this one area. So, and it's, if you put an actual, let's say like a triangle face or like a plate, it really shows that these are right next to each other and they're within one face. So if I were to draw it in this format, it's in this corner, and this corner. So top, left, right of the front. It could be top, left, over here where the A stands and here, or it could be this area. The whole point is, if I were to put like a face there or a plate there, a triangular plate there, it should line up with, in every vertices, with the transition metal that are the same. On this side, however, it's a little different. The ligand either could be on the top or the bottom, but the other one must be in 180 degree of each other on opposite ends. Okay, so these are all 90 degree of each other, but this one is 180 degree from each other, or two of them needs to be on opposite. It kind of passes through this whole geometrical shape of the octahedral complex. So this one is considered to be FAC, F-A-C, and the other one is known to be MER, geometric isomer. And this is another example. It would be a cobalt with ammonium and chlorine. So if I were to relabel this, erase this guy. If I were to relabel this, then we can relabel this middle as the cobalt. That's our transition metal. And say the chlorine is the purple guy. So the purple guy is all here. And you can see the purple one is the one that's going to sort of determine the whole phase. And notice it's 3, not 2, because if it has only 2 chlorines, then probably we're going to be dealing with cis and trans, but we're not. And this one has ammonia on every corner. So essentially, you can look at both ammonia and chlorine, since there's 3 to 3, to determine the FAC and MER. And that's all you really need to look at one of the 3 of the same thing. Okay. All right, let's do a learning check. It says a compound has a chemical formula of cobalt, water, and chlorine, and tetra water, and then there's dichlorine. Draw cis and trans isomer. So we're going to go ahead and try the cis first. We're going to do cobalt in the middle, and we're going to put water all around it. So let's be a little bit careful and be thoughtful where the water goes. So going back, it's H2O. Coming forward is also H2O. I'm going to have another one that goes down, that's H2O. And going back, H2O. So we're sort of exhaustive of all the H2Os. So what comes out in the front are the rest, which is chlorine here, and then the top is chlorine. So we know that this is 90 degree of each other, so this works, and this is cis. So you try it for trans and come back and check the key. So here's a trans isomer, and you see how the chlorines are in opposite of each other and they're 180 degrees from each other. You could have drawn the chlorine to be over here and the opposite side over here, or maybe 2 of them going in this one and this one. It really doesn't matter. The point is that they need to be 180 degrees apart, whereas for cis it needs to be only 90 degrees apart. Let's do another one. A compound has a chemical formula of cobalt, H2O, Cl3. Draw FAC and MER isomer. So let's try FAC first. And we have our cobalt. And in order to have FAC, we need to make sure that 3 of the exact same ligand has to be in the vertices of the one that has a triangular face. So for example, if this is up and this is chlorine, then the ones that's coming out at you, 2 of the ones that are coming out at you better be chlorine. And the rest is water. We could have switched spots with H2O. We could have swapped places with water and have water be the determination of FAC and MER, and that would have been the same thing. And then now you try the MER and then come back. And here is a key. So here's my chlorine, 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 water, water, water. Now let's go into enantiomer. Enantiomers are type of a stereoisomer. Okay, they're type of a stereoisomer, and there's only there's no categories of enantiomer. It's just that enantiomers are compounds that are superimposable mirror image of each other. So if I look at this metal and another metal, and imagine that this right here is the mirror. Okay, it means that they're mirror image of each other. This NH2 and this NH2 are exactly the same. This NH2, NH2, and so on and so forth. Now, this image really shows that they are actually not the same, because if I were to take this entire image and then place it on top of here, okay, no matter what I do, they're going to have a different, they're not going to be right on top of one another. And I'm going to show you a demonstration of what that looks like. So I have these models here that are superimposable for each other. So these two models here. See, the purple ones are on top, and then we have the red ones on that's coming towards you. We have the green ones that are kind of on the plane, and we have a yellow one in the back. So they're mirror of each other, right? The left and the right one, they're mirror of each other. The thing is, if I were to, this is same for, this is a tetrahedral. This will work also for octahedral. Just depends on what kind of attachment there are. Now, if I were to line them up so that they are you might say they're exactly the same. Well, they're quite not. So let me line this purple one and the red one, okay? So if I line them up together like this, the purple ones are on top, the red ones are on the bottom. But in the back, you will see how the green and the yellow are not lined up, right? You see the green one here, and there's the yellow one here. Green one here and yellow one here, and green one here and yellow one. They're not lined up. Okay, so let's line up the green and the yellow ones. So if I were to line up the green and the yellow ones, okay, if I line them up, well, the purple and the red, they don't line up. So we can see when they are looking at each other as if they're looking at the mirror, they look like they're exactly the same. But if I were to put on really top of one another, they're not the same. So they are an isomer in that they have same attachments, right? These are stereoisomers. They have same attachments, but they're enantiomers. They're mirror of each other. We can't say this is a FAC and MER or the geometric isomer cis and trans because most of the parts of these guys are going to, they're not in mirror of each other, right? FAC and MER, they're not in mirror of each other, nor cis and trans. They're by angles are different. So they're not quite geometric isomer. They're mirror image of each other. So we're going to do a learning check. Draw enantiomer isomers of cobalt, NH3, Cl2, and F. Okay, so we're going to go ahead and draw one side which has cobalt and the other side, and then here will be my mirror, and the other side will also have a cobalt. If I have a chlorine that goes on top, then I better have a chlorine that goes on top too. Well, I have another chlorine that's going back, and so is this one that's going back. And another one coming forward, and this one is also coming forward, and that's going to be my other halogen, which is fluorine. Then I will draw the rest in of ammonia. And same here. So in this portion, if I were to again try to line it up, the two molecules together, you're not going to get the same thing. Even if the cobalts are lined up, maybe two of the chlorines are lined up, you'll see that like the fluorine will not line up. It'll be where the other one has ammonia. So because of that, this is an enantiomer, a type of a stereoisomer.